Okay, today we're going to talk about parent functions that you should totally know, and then we're going to talk about how to deal with transformations of those parent functions. So first, we're going to talk about the parent functions that you should know. The first one that you should know how to work with is a quadratic function. So when we talk about a quadratic function, I'm talking about f of x equals x squared. And that's your basic parent function, right? Now, what I want to teach you is that each parent function can be easily graphed with a certain number of points. In the case of a quadratic function, what I want you to pick is 0 as your center point, and I want you to pick 2 points to the right of it and 2 points to the left of it. So I'm going to go x equals 1 and x equals 2, x equals negative 1 and x equals negative 2. So when you square those x values, you get 4, 1, 0, 1, and 4. And so those 5 points will inform what your parent graph is going to look like. Okay, so I'm going to graph those 5 points. I'll just use red, I guess. So my vertex, the center point is 0, 0, and then I go 1, 1, and 2, 4. And on the left, negative 1, 1, negative 2, 4. And so it curves up like this, and you have your U-shaped parabola, right? So that's the parent function for a quadratic, or the parent graph for a quadratic function. Now let's look at a cubic function. So we're talking about f of x equals x cubed. So again, I want to have some points that I could use in order to see what this looks like. So I'm going to pick, again, 0 for my middle point, 1 and 2, negative 1 and negative 2. So when you cube negative 2, you get negative 8, negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So when you graph this parent function, one, two, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So your points, middle point is 0, 0. To the right, we go 1, 1, and 2, 8. So that one's going to increase very quickly. And then to the left, negative 1, 1, and negative 2, 8. So that one's going to decrease very quickly. And there's your graph. Next, let's look at the square root function. So that's f of x equals the square root of x. Now this time, with the square root function, and actually let me go back here. Oh, it won't let me erase it. So for the square root function, you're not going to pick any negative values for x because that's not in the domain of the function. So we're going to start from x equals 0, and then we're going to pick values of x that make sense, like x equals 1 and x equals 4, because I want to take the square roots of those numbers. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. And so if you graph this, now you get your starting point is 0, 0, and it doesn't go left. It only goes right. So 1, 1, and 4, 2. So it's a half sideways parabola is what it looks like. Next, we're going to look at this one. This one, it does come up from time to time, so you should know it. It's the reciprocal function, which is f of x equals 1 over x. So if I make this table of values, I'll pick 0 in the middle, but this time 1 divided by 0 is undefined. And so I'm going to pick x equals, how about 0.5, 1, and 2, and then negative 0.5, negative 1, and negative 2. So 1 divided by negative 2 is negative 0.5, 1 divided by negative 1 is negative 1, 1 divided by negative 0.5 is negative 2, 1 divided by 0.5 is 2, 1 divided by 1 is 1, 1 divided by 2 is 0.5. So what happens with this one when you graph it is because you have this at 0, the function's undefined, you're going to have a vertical asymptote on the y-axis. And then when you graph your points, so I'm going to go 1, 2, 1, 2, 1, 2, 1, 2. You're going to have -2, -0.5, -1, -1, -0.5, -2. And then you're going to have 0.5, 2, 1, 1, and 2, 0.5. So you can see this graph looks like this. Okay, that's your reciprocal function. Next, let's go with that. Next, we're going to look at your absolute value function. And in particular, it's the absolute value of just x. So that's f of x equals the absolute value of x. So again, for this, I'm going to pick 0 as my middle value. I'm going to pick x equals 1, x equals 2, x equals -1, x equals -2. And the absolute value of each of those x values is going to be positive. So when you graph this thing, 1, 2, 1, 2, 1, 2, you're going to have your 0, 0, vertex, 1, 1, 2, 2, -1, -1, 1, -2, 2, and you have this v function. And then there's one more that they mention in the book on page 46, and it's called the greatest integer function. I'm not going to really talk about that one because it's a very specialized case and it doesn't really come up that often. Okay, so for each of these functions, you should be able to describe the characteristics of the graph. All right, so let's see here. I guess I can write it on the side here. So for the quadratic function, I'll do all the characteristics in blue. For the quadratic function, you can see that your domain is all real numbers, right? X can be anything. But your range, the lowest point is 0. So it goes 0 to infinity. Let's see, what else do we need to know? Intercepts. So both the x and the y intercept is 0, because you have that 0, 0 point. It has y-axis symmetry. And as far as the end behavior goes, the limit as x goes to -infinity of the function is positive infinity, and the limit as x goes to positive infinity of the function is also positive infinity, because both sides go up. Okay, so here I'll kind of box this away. Oops. I'll box this, and that's your quadratic function. Okay, let's look at our cubic function. For our cubic function, our domain is all real numbers, so -infinity to infinity. Your range is also all real numbers, because it goes down and up forever. Your x and y intercept are both 0. It has origin symmetry. And as far as the end behavior goes, the limit as x goes infinitely to the left of the function is -infinity, and the limit as x goes infinitely to the right of the function, that side goes to positive infinity. So these are your characteristics of your cubic function. Okay, for square root, this time your domain, it starts at 0 and goes to infinity. Your range also starts at 0 and goes up to infinity. Your x and y intercept are both 0. You have no symmetry. And then for end behavior, you only have one side that goes forever, and that's to the right. So the limit as x goes to infinity of this function is infinity. So there's your characteristics of the square root function. Okay, the reciprocal function. So the reciprocal function has an interesting domain. it goes from negative infinity to 0, and then from 0 to infinity. And the range does the same thing. Negative infinity to 0, and then 0 to infinity. This thing has no intercepts. And it does have symmetry. It has origin symmetry. And then as far as end behavior goes, the limit as x goes to negative infinity of the function approaches 0. Likewise, as x approaches positive infinity, so infinitely to the right, the function also approaches 0. So here is your reciprocal function characteristics. And then finally, for absolute value, we have your domain is all real numbers. Your range, however, starts only from 0 and goes to infinity. Your x and y intercepts are both 0. It has y-axis symmetry. And then the end behaviors both sides. So as you go to the left, the function goes to infinity, and also as you go to the right infinitely, the function goes infinitely high. So here are your characteristics for your absolute value function. So these are the 5 real big ones that you really have to be familiar with. Once you're familiar with them, now you could talk about transformations on any one of those at any time. So now let's talk about transformations. The first type of transformation or change to the graph that we're going to talk about is called a translation. A translation basically is a shift of the entire graph either up or down or left or right. Okay, so you're not changing the shape of the graph. That's why they call this a rigid transformation, because the shape of the graph maintains the same. Okay, so the basic idea that I want you to understand, and this is really a broad kind of general statement, and your book doesn't quite put it this way. So this is more like my interpretation of transformations. So I'm going to call them Mikasa's transformation, and I'll call them principles because they're not really rules, but they're just kind of principles. Okay, so the first principle is this: if you have a number that is directly applied to x, it affects the graph horizontally. So if the transformation is directly applied on x, it is horizontal in nature. So in other words, it'll affect the x value, which makes sense, right? And then vice versa, if the transformation is directly, or not directly, is applied outside the parent function, the transformation is vertical in nature. And I'm going to need more space than this. Let me get rid of this box here. I guess I could just get rid of the bottom. Okay. So that's principle number 1. Principle number 2 is vertical changes are direct and horizontal changes are opposite what they appear. Okay, so just keep these 2 principles in mind, and I'll explain how they apply to each of the things we explore. So translations, which are shifts up and down. Let's take a look, let's say at, suppose we have, for example, f of x equals x squared, okay? So let's say that's the parent function we're dealing with. Well, here's the deal. If we have some other function g of x, and it's equal to x squared, but then plus, I'll just say 3, what is that going to do to the graph? Well, the plus 3 occurs outside of the original function, so I know it's going to be vertical. And it says plus 3, so vertical changes are always exactly what it says they are. So this is going to shift the graph up 3 units. Okay, well, what if my g of x function instead has x squared and then minus 3? Well, this is just going to take your x squared graph and move everything down 3 units. Well, how do you move it left or right? Well, left or right means that you're changing the x value, right? So therefore, if you're just changing the x value and not changing the function, you're changing the x value. So if I put a plus 3 here, and now here's where my principles come into play. So you see that I'm putting a plus 3 directly on the x. So I know I'm shifting the graph horizontally. But my second principle says that it's always the opposite of what it appears. So instead of going 3 to the right, which is maybe what you would think because it's positive, it's actually going to go to the left. So this is left 3 units. And then, of course, if I have inside the parentheses a minus, then this will move things to the right 3 units. Okay, so those are the 4 types of translations. There's shift up, shift down, shift left, or shift right. Okay, so let's see if you understand that in the context of a problem. This is example 2 in your book. So this time we're starting with the parent graph, absolute value of x, and they want us to graph g of x equals the absolute value of x plus 4. All right, so I look at this problem and I see a plus 4. So first thing I'm going to do is I'm going to identify what that plus 4 does to my parent graph. So this plus 4 is going to move everything up 4 units. All right, well, that's actually pretty easy because I know what my absolute value graph looks like. So if I shift everything up 4 units, this is going to be my new vertex, right? And I know that the way my absolute value graph looks is we go 1 over, 1 up, and then we go 2 over, 2 up. And we do that on both sides. So 1 over, 1 up on this side, the left, and 2 over, 2 up on this side. And that gives you all 5 of your original points shifted up 4 units. All right, let's look at another. What if your function says g of x is equal to the absolute value of x plus 3? Well, now this time, since the plus 3 is inside the absolute value, I know I'm going to shift either left or right. But because it's a plus, I know that means I'm going to go left 3 units. So when I graph this one, I'm going to shift it 3 units to the left, and that's where my vertex is going to be. And then I know that the way that my absolute value graph goes is it's going to, again, go 1 over, 1 up on both sides, and 2 over, 2 up on both sides. So these are going to be my 5 basic points. And it's going to make my V graph. Let's look at one more. What about if we have g of x equals the absolute value of x minus 2 minus 1? All right, well, now we have 2 transformations. I have this minus 2 on the inside, so that's going to shift it 2 units to the right. And then I have this minus 1 outside, so that's going to shift it down 1 unit. Okay, so when I make my graph, Let's go 2 to the right and 1 down. So this is going to be my new vertex. And then from that vertex, I know I go 1 over 1 up, 2 over 2 up. So 1 over 1 up this way, 2 over 2 up this way, and then 1 over 1 up to the left, 2 over 2 up to the left. So that gives me my new absolute value graph after the transformations. All right, next, let's talk about reflections. So this is a second type of transformation. So basically, if you have a negative that's either applied directly to the x or to the function itself, that's going to flip the graph either over the x-axis or the y-axis. So let's break this down and I'll explain it. So again, this time I'm going to use, for example, f of x equals the square root of x. Okay, so remember what the square root of x looks like and just consider that. So let's say I want to find out what happens to g of x if I put a negative outside of the square root. So what is that negative doing? Where is it? It's on the outside. So remember, if your transformation is on the outside, it's going to affect the graph vertically. So that means this graph is going to reflect on the x-axis. It's going to flip the graph over the x-axis. So if I graph this thing, right, my original graph, I know what it looks like. Well, now I'm going to flip it over the x-axis. So it's going to be starting here. I'm going to go 1, 2, 3, 4, 1, 2. So I'm going to go 1 over 1 down instead of up, and 4 over 2 down instead of up. So this is going to be the graph of y equals negative square root of x. Well, what if I have the square root of negative x? Well, this time, where is the negative? Where is the negative multiplier? It's in the inside of the function, and it's directly applied to the x. So when it's applied on the inside, it's going to flip the graph horizontally. And so if you flip the square root graph horizontally, it's going to reflect on the y-axis. So if you graph this thing, this is what it's going to look like. It's going to go this direction instead. So it's going to go still start at 0, 0, but now it's going to go left 1, up 1, and left 4, up 2. So this is your graph of your square root of negative x. So that's how you deal with reflections. All right, let's take a look at a couple of examples. Okay, let's look at example 3a. They want us to describe if f of x equals x squared is our parent function, right? That's our parent function. Then how are g of x and f of x related? And then how do we write the equation? So I see two things happening with this g of x. I see that instead of the parabola opening up, it opens down, right? So that means it's been flipped over the x-axis. Or you could think of that as a vertical reflection. So I see a vertical reflection. And I also see that the vertex appears to have been moved. So it's been shifted, what is that, like 2.5 units to the right? So about 2.5 units right. Okay, so now how do I take those two observations and put them into an equation? Well, it's going to go like this. So if I have a vertical reflection, that means it's affecting the y value, so the negative has to be on the outside. So I'm going to put a negative outside the x squared. But I also see that I'm shifting the graph 2.5 units to the right. So I have to put inside the parentheses with the x a minus 2.5. So that's how you write the function. Right, so it's kind of like working backwards from what we were doing previously. Now let's look at B. So in B, what observations do you make? Well, again, I see that the graph has been flipped, so instead of going up, it's going down. So again, I see that vertical reflection. And then as for the vertex, it looks like the vertex has been moved up 2 units. So I shifted up 2 units. All right, let's put that together. So my new function there has to be negative x squared and then plus 2 outside. Remember, because up down is a vertical transformation, so you put that outside of the x squared. All right, next we're going to talk about, the book calls them dilations. I call them stretches or shrinks. Okay, so stretch or shrink. And really, actually, instead of shrink, let's use the word compress. You could think of it as shrinking it, but I like to think of it as compressing it. Okay, so the easiest way to talk about this is to, again, use my principles of graphing and transformations. So suppose we have, let's do absolute value this time. So let's say we're looking at f of x is the absolute value of x. Well, if g of x is, let's say, 2 times the absolute value of x, what is this 2 going to do to the graph? Well, it's a multiplier, right? So it's multiplying something times 2, and that 2 is on the outside of the function. So it's going to be a vertical multiplier, which means that all the y values are going to get stretched out by 2. So this is a vertical stretch by a factor of 2. Now what if that number was less than 1? Let's say it's like 1/3 the absolute value of x. Well, in this case, instead of the y values being twice as much, like it is in the 2 situation, it's only going to go up 1/3 as high. So that means that the y values are getting smushed. So this is a vertical compression or shrink by a factor of 1/3. So if you're thinking about the graph of these, this graph, instead of going up 1 and up 1, or over 1 and up 1, or over 2 and up 2, it's going to double it on both sides. So it's going to go from 0, 0, over 1 up 2, over 2 up 4. So it's double what it usually does. That's this graph, right? And that's a vertical stretch. You could see that it's a skinnier looking graph because it's been stretched out. Now in this case, the y value, so if this is 1 and this is 2, the y values are only going to go up 1/3 as high. So for 1 over, it's only going to go up to here. And for 2 over, it's only going to go up to here. Same thing on the other side. So this, you could see it's a flatter or compressed graph from a vertical perspective, right? It's like the graph got smushed vertically down. So that's how you do vertical stretches and compressions. Well, what about horizontal? So let's say I have g of x equals the absolute value of 2x. Now, in some sense, could you pull out the 2? Yes, you could. But because I want to just highlight the principles of my graphing techniques, let's just look at it the way it is. So this time you have the 2 multiplier on the inside. So it's going to affect the graph horizontally. But remember, I told you that anything that affects the graph horizontally is going to be the opposite, or in this case, the inverse of what it appears. So instead of multiplying the x values by 2, they're going to divide the x values by 2. Or in other words, they're multiplying the x values by 1/2. So horizontally, from a horizontal perspective, this is actually going to be a horizontal compression by a factor of 1/2. Now, what does that look like from a graphing perspective? Well, let's think about that. Oops. So let's think about that. Normally, your x values are x equals 1 and x equals 2. or x equals -1 and x equals -2, and then you go up 1 or up 2. But now you're only going to go half as far for your x because your x values are being compressed. So you're only going to go half a unit to the right and 1 up. And instead of going 2 units over, you're only going to go 1 unit over to go 2 up. Likewise, instead of going 1 unit to the left, you're going to go half a unit to the left and 1 up. And instead of going 2 units to the left, you're going to go 1 unit to the left and 2 up. So some of you may be saying, well, wait a minute, that looks exactly like the vertical stretch graph. And you're right, but we're just looking at it from a different perspective now. Now we're looking at it from the x perspective instead of the y perspective. All right, one more example. Let's say you have g of x equals the absolute value of 1/2 x. So now what's this 1/2 inside gonna do? Well, it's horizontal because it's inside, and it's the inverse of what it appears. So instead of multiplying by 1/2, you're gonna divide by 1/2. And dividing by 1/2 is like multiplying by 2. So this is gonna be called a vertical stretch, or sorry, horizontal stretch times 2. So now, when you graph it, your vertical is not going to change. So you're still going to go up 1 and up 2. But now your horizontal is going to get stretched out. So instead of only going 1 unit to the right and left, you're going to go 2 units to the right and left. So 2 units over, 1 unit up is 1 point, right? Same on the other side. And then now instead of going 2 over and 2 up, you're going to go 4 over and 2 up. So that's that point and that point. And so this is what it looks like when you stretch the graph horizontally. And does it look similar to a vertical compression? Well, yes, right? If you smush a graph vertically, it looks like the horizontal has been stretched, and vice versa. Okay, this is a pretty long video, but it has important information in it, so I hope you're hanging in there. I am going to skip a couple examples in the book, and I'm going to go to now talking about absolute value. Now, if you think about absolute value, what does absolute value do when you think about absolute value? Now, most of you are thinking that what absolute value does is it changes whatever number is inside, it changes it to a positive number, right? And if it was already positive, then it just stays positive. But if the original number was negative, then it turns it positive, right? So that's one way to think about it, because it's distance from 0, so it's always a positive measurement. But I want you to think about this now from a different perspective. Let's think about it from a graphical perspective. What does it mean for the y values to always be positive? Well, let's think. We know that y equals x. We know this graph looks like this, right? Well, so that's the red y equals x. So what happens if I do y equals the absolute value of x? What happens to the graph? Well, this equation right here guarantees that the y value has to be positive. So basically all you're going to do is you're going to take all of the negative y values, so all of these y values, and it's going to get flipped over the x-axis. So your absolute value graph is simply going to be, instead of this side going down, it's going to be like this. And then the right side was already positive, so it just stays right where it is. So that's the graph of absolute value of x. So again, anytime you have an absolute value on a function, any of the negative parts of the graph are going to get flipped over the x-axis. Let me write that down. So if you have an absolute value of some function, any parts of f of x that are negative, and what I mean by negative is below the x-axis, will be flipped or reflected on the x-axis. Okay, so that's an important graphical principle. So therefore, Let's do a little drawing again. Say your function, say your y equals f of x graph looks like this, okay? Let's say it looks like this. So if that's what y equals f of x looks like, what will y equals the absolute value of f of x look like? So think about it now. All of the parts that are negative have to get flipped over. So I'm going to highlight the negative parts. These are the parts that are below the x-axis, right? Those are the negative parts. So the two wings are going to stay the same. So on the left, you're still going to have this piece going down like that, and on the right, you're still going to have this piece going up like that. But now the middle piece is going to get flipped over. So instead of kind of curving down and then back up, now it's going to bounce and it's going to curve up and then come back down. So this is what the graph of the absolute value is going to look like. All the negative parts get flipped. Alrighty? Okay, that's really the main thing. There is another one where there's a horizontal absolute value, but I think I'm going to skip that for you guys because it's not really that important. So this is kind of the main thing I want you to get at the end of this lesson. All right, see you next time in class.